Welcome back to the deep dive. Today, we're putting on our chemistry hats
Definitely.
because we're tackling really the fundamental architecture of how matter changes. The core concepts. We're deep diving into chemical reactions, the energy side of things, and the math bit stoichiometry that lets us predict what's going to happen.
Yeah, the quantitative part.
Our mission today, to kind of cut through the maybe more complex jargon from the source material and pull out the key insights, we want to give you the essential framework
Right.
from why molecules even collide in the first place, all the way to the calculations you'd need for a real chemical process.
That's a good way to put it. And we've sort of broken this down into three main pillars, haven't we?
Yeah.
First, the energy dynamics.
Yeah.
Exothermic, endothermic, the push and pull.
Okay.
Second, the evidence. How do you know a reaction actually happened? What are the signs?
The observable stuff.
Exactly. And finally, the math, the language of chemistry, really.
Yeah.
Moles, formulas, and reaction yields, crucial stuff.
All right, let's unpack that first bit then, the most basic question. Why?
Yeah.
Why does a reaction happen at all? What are the bare minimum conditions?
Collision theory.
Collision theory.
Yeah.
Yeah, it's quite elegant, actually. It gives us a very clear three-part checklist. It tells us molecules don't just react passively, they need to interact successfully.
Okay, so what's on the checklist?
Well, requirement number one is kind of obvious. They have to physically collide, lump into each other.
Right.
But that's the easy part. Requirement two is critical. They must collide in the correct orientation, or, an appropriate one.
Like puzzle pieces?
Exactly like puzzle pieces. You can bang them together all day, but unless the reactive parts line up just right, nothing.
Makes sense.
Yeah.
Geometry matters.
Absolutely. And that brings us to number three, the non-negotiable bit. Sufficient energy.
Ah, the energy hurdle.
Precisely. The collision needs to have enough kinetic energy to equal or even exceed what we call the activation energy.
Right. Without that minimum energy kick, even perfectly aligned molecules will just sort of bounce off each other. No reaction.
Okay, that energy requirement leads us straight into the heat aspect, doesn't it? Exothermic, endothermic. We hear these terms all the time. Can you clarify, based on the sources, what's happening with the bonds? Breaking versus forming.
Yeah, this is a common sticking point, but the sources are super clear. It always takes energy to break a chemical bond. Always. That's an endothermic process. You have to put energy in.
Okay, energy in to break.
Right. And conversely, when atoms come together and form a nice, stable new bond, energy is always released. That's exothermic. Energy out.
So whether a reaction is overall endo or exo is just which one wins, the breaking or the forming?
Spot on. It's a net calculation. In an endothermic reaction, you needed more energy to break the old bonds than you got back when the new ones formed.
So it feels cold, maybe, absorbs heat.
Exactly. The system absorbs energy from its surroundings. You might see that energy written as a reactant in the equation or shown as a positive delta H value, change in enthalpy.
Got it. And exothermic.
Exothermic is the opposite. You get more energy released when those strong new bonds form than you had to put in to break the weaker old ones.
So net energy release feels hot.
Usually is heat, yeah, or sometimes light. And you'll see that energy written on the product side of the equation or as a negative delta H.
And we often see those potential energy diagrams, right? Those graphs that show the energy path.
Yeah, those are great visualization tools. They map out the energy landscape, showing the reactant's energy, the product's energy, and that big hump in the middle, that's the activation energy.
And the peak of that hump is the activated complex.
That's it. That super unstable, high-energy, fleeting arrangement of atoms right at the transition point.
Yeah.
And those diagrams also show nicely how a catalyst works.
Right, the catalyst. How does that fit in?
Well, a catalyst doesn't change the start or end energy levels. What it does is provide a different pathway, a shortcut, if you will, with a lower activation energy hump.
Ah, so it makes it easier for molecules to meet that third collision theory requirement.
Precisely. Easier to get over the energy barrier, so the reaction goes faster. Doesn't change what you get, just how fast you get it.
Okay, theory makes sense. Now let's shift to the practical side. How do you know? If you're doing an experiment, what's the proof that a chemical change actually occurred, not just, say, mixing stuff together?
Good question. The sources lay out 4 key observable signs. Evidence, basically. First sign, you might see a precipitate form.
A solid appearing out of nowhere.
Well, out of a solution, yeah. An insoluble solid forms and often settles out. You need your solubility rules to predict if that should happen.
Okay, precipitate, what else?
A second, formation of a gas. Bubbles, fizzing, effervescence, that's usually pretty obvious,
Hard to miss bubbles.
right? Third is a definitive color change. But there's a catch here.
Ah, I remember the source's warning about this. It's not just getting lighter or darker, right?
Exactly. That's the key distinction. If you just add water to, say, blue copper sulfate solution, it gets paler blue. That's just dilution, a physical change.
Right.
A chemical color change means a new substance with a genuinely different color has formed, like clear liquids mixing to make something bright yellow. That's a sign of new bonds.
That's a really important point for anyone learning this. Okay, precipitate, gas, real color change. What's number 4?
Number 4 brings us back to energy, a temperature change.
Ah, endoexothermic again?
Yep. If the beaker gets noticeably hot, that's exothermic proof. If it gets cold, that's endothermic proof. It's direct physical evidence that bond breaking and forming with their energy changes have happened.
Okay, so we've seen the signs, reaction confirmed. What's the very next fundamental step? Something about conservation.
You got it. The law of conservation of mass. Matter isn't created or destroyed in a normal chemical reaction. Atoms just rearrange.
Meaning the equation has to balance. Same number of each type of atom on both sides.
Absolutely essential. And while balancing can sometimes feel tedious, the sources offer some really handy tips.
Practical shortcuts. Always good.
Definitely. First, always remember your diatomic elements. Hydrogen, oxygen, nitrogen, fluorine, chlorine, bromine, iodine. They exist as pairs, like O, H hero, when they're on their own, not in a compound.
Yeah.
Easy mistake to make.
Right. H is H, O is O.
Exactly.
Right.
Second big tip, polyatomic ions. Things like sulfate, Se or O, or nitrate. If you see the exact same group on both the reactant and product side, treat it as a single unit when you're counting and balancing. Don't break it down into individual sulfurs and oxygens unless you have to. Saves a ton of time.
Ah, balance the whole chunk.
No.
Smart.
And one more, especially for combustion reactions, burning things in oxygen, there's a neat, even odd trick for balancing the oxygen atoms.
Oh, yeah.
Yeah. Sometimes after you balance the carbons and hydrogens in the fuel, you end up needing, say, 7.5 oxygen molecules on the reactant side.
Yeah.
But you can't have half a molecule.
Right. O-Rose comes in pairs.
So the trick is just double the coefficient of your fuel molecule, the hydrocarbon, usually. That makes all the carbons and hydrogens even, which guarantees you'll need an even number of oxygen atoms on the product side, meaning you can use a whole number coefficient for O-Rose on the reactant side. Works like a charm.
That's genuinely useful. Okay, so we balance it. Now, what about types of reactions? The sources list the main categories, right?
They do. The big 5 are usually listed as synthesis, A plus B, AB, decomposition, AB, A plus B, single replacement, A plus BC, AC plus B, double replacement, AB plus CD, AD plus CB, the combustion.
And combustion is usually something reacting with oxygen, producing heat and light.
Typically, yeah.
Yeah.
Especially the complete combustion of hydrocarbons, things with carbon and hydrogen, maybe oxygen too. That always produces carbon dioxide, COO, and water vapor.
Gotcha. And the sources mention that acid-base neutralization is really just a specific kind of double replacement.
That's right. An acid, like HCl, reacts with a base, like NaOH, and they swap partners to form a salt, NaCl, and water, HOH. It fits the double replacement pattern perfectly.
Okay. Now, for single and double replacement, just because you write it down doesn't mean it happens, right? There are prediction rules.
Absolutely critical point. For single replacement, you need the activity series. This is basically a list that ranks elements, usually metals, by their reactivity.
So a more reactive element can kick out a less reactive one.
Exactly. If element A is higher on the activity series than element B in compound BC, then A can replace B. If A is lower, then no reaction. Simple as that.
Okay, activity series for single replacement. What about double replacement?
For double replacement, the driving force is usually the formation of something that removes ions from the solution. So you need your solubility rules.
Ah, to see if a precipitate forms.
Right. After you swap the partners notionally, AB plus CD, AD plus CB, you check the solubility rules for the potential products, AD and CB. If both potential products are soluble, aqueous, AQ, then everything just stays dissolved as ions. Nothing has really changed chemically.
So no precipitate, no gas formed, no water formed?
Then effectively no reaction occurs. You just write NR, or no reaction.
That makes sense. Okay, that covers the types and predicting them. Now let's shift gears to the math, the quantitative side. Analyzing what's in a substance first.
Right, composition. This really hinges on understanding the mole concept and being able to convert between grams, moles and the number of particles, atoms, molecules, ions, whatever you're dealing with. That's the foundation.
Avogadro's number and molar mass territory.
Exactly. Once you get that translation down, you can figure out things like percentage composition by mass. What percentage of water's mass is hydrogen versus oxygen.
And you can use that practically, right? Like figuring out how much nitrogen is in a bag of fertilizer.
Absolutely. If you know the percentage in the total mass, it's just proportional reasoning to find the mass of the specific element you're interested in. Very useful.
And this also lets us figure out chemical formulas from experimental data.
Yes. If you have mass data or percent composition data for an unknown compound, you can calculate the simplest whole number ratio of atoms in it. That gives you the empirical formula.
The simplest ratio, but maybe not the actual formula.
Correct. For example, both acetylene, CH, and benzene, CHA, have the same empirical formula, CH. To find the true molecular formula, you need one more piece of information. The compound's molecular weight, its actual molar mass.
And you compare the mass of the empirical formula to the known molecular mass.
Exactly. You see how many empirical formula units fit into the actual molecular mass, and you scale the empirical formula up by that factor.
Okay, that nails down composition. Now let's broaden the view from one substance to the whole reaction. Proportions within the reaction itself. Stoichiometry?
Stoichiometry. Sounds intimidating maybe, but it's really just recipe math on a massive scale. And the key, the absolute key, comes from the balanced equation.
The coefficients, the numbers in front.
Yes. Those coefficients aren't just for balancing atoms, they represent the essential mole ratios. That's the heart of stoichiometry.
So if the equation says 2H euros plus O euro, 2H euro.
It means you need exactly 2 moles of hydrogen molecules for every 1 mole of oxygen molecules to produce 2 moles of water molecules. That ratio, 2 to 1 to 2, holds true whether you're talking about moles or millions of moles or just molecules.
And that lets you calculate amounts.
But it's precisely. If you know how much you have of one substance in the reaction, say grams of hydrogen, you can use the mole ratio from the balanced equation to figure out exactly how much oxygen you need or how much water you can theoretically make. You can calculate it in moles, grams, number of particles, even volume if it's a gas at STP.
STP being standard temperature and pressure. Okay, so that calculation gives the perfect ideal result, the theoretical yield.
Yes, what the math says you should get if everything goes perfectly.
But lab reality is often different.
Yeah.
Which brings us to limiting reactants and yields.
Right. In the real world, especially in industry, you rarely mix reactants in the exact perfect stoichiometric ratio from the balanced equation. Usually, one reactant gets completely used up before the others.
And that one is the limiter.
That's the limiting reactant. It dictates the maximum amount of product you can possibly form. Once it runs out, the reaction stops, even if you have tons of the other reactants left over.
Those leftovers are the excess reactants.
Exactly. The source material often uses particle diagrams, little drawings of molecules, which are great for visualizing this. You can literally see one type of molecule disappear while others remain.
And this difference between the theoretical maximum and what you actually get in the beaker or the reactor, that's where yield comes in.
Correct. The theoretical yield is your perfect calculation. The actual yield is the amount of product you physically measure after you've done the reaction, collected the product, purified it, etc.
And the comparison is the percent yield.
Yes. Percent yield is simply actual yield, theoretical yield, 100%. It tells you how efficient your reaction actually was.
And this is huge in industry, isn't it? Not just about being tidy in the lab.
Oh, absolutely critical. Think about pharmaceuticals or materials science. Maybe one reactant is incredibly expensive and another is dirt cheap.
Ah, so you'd make sure the expensive one is limiting.
You bet. You'd deliberately use the cheap reactant in excess to force as much of that expensive limiting reactant as possible to convert into product. You want to maximize the conversion of the valuable stuff, aiming for the highest possible percent yield based on that limiting reactant, even if you waste some of the cheap excess stuff. It's an economic calculation.
That's a great insight. So a low percent yield could be due to side reactions, losing product during filtering, the reaction just not going to completion. Lots of factors.
All of the above. It's a measure of how well reality matched the ideal chemical equation.
Wow. Okay, so we've really covered the journey. From the microscopic checklist of collision theory, why things react, to spotting the signs, balancing the books with the law of conservation of mass, and then using stoichiometry and yield calculations to predict and measure outcomes, right down to the industrial bottom line.
It's quite a comprehensive picture when you put it all together.
It really is.
And maybe a final thought to leave listeners with, tying back to something we mentioned earlier, visualization. We've talked about a lot of math, right? Empirical formulas, mole ratios, limiting reactants.
Yeah, on the quantitative side.
But think about this. How much predictive power, how much understanding about those mole ratios, or which reactant is going to run out first, or roughly how much product you'll get, how much of that can you get just by looking carefully at a well-drawn particle diagram before you even pick up a calculator?
So visualizing the molecules themselves can give you a strong intuitive grasp of the stoichiometry.
I think so. It's a reminder that all these numbers represent actual physical particles interacting. It really reinforces the connection between the microscopic world and the macroscopic calculations. Something to ponder.
That is a powerful connection. Visualizing the unseen. Great thought to end on. Thanks for joining us for this deep dive.